Okay, and then if you want to solve a nonlinear system, what do? You wrap one level of iteration out of that. Then that's what we'll talk about next. Then you have one for I Newton iteration. Wrap it even outside of that. So you have a for loop within a for loop within a for loop within a for loop. Right, that's one of the actually pretty popular way of solving a very large nonlinear system that comes out of a discretization of a nonlinear PDE. Okay, so for Newton's method, I want to spend a little bit of time just telling you the gist of that. So Newton's method, I think, is actually one of the most powerful methods out there. The idea is very simple. The idea, you can explain it for a scalar function with just a few words. But the Newton's method, they apply to system of equations, right, which is what we are going to be used here. It even applies to infinite dimensional problems, right? Not the ones you solve in a computer, but like if you do mathematical analysis, there is Newton's method or implicit function theorems, really, that works on functional spaces in infinite dimensions. So in one dimension, we just we want to solve fx equal to 0. So that's a typical nonlinear equation we ended up having to solve. And if this is fx, this is x, can be a nonlinear equation. We want to find whatever x that makes fx equal to 0. And the idea is if we can evaluate f, and if we can evaluate the derivative of f, then the Newton's method is very powerful. It involves what we have been used a lot in this class, the the Taylor series expansion. So you pick an arbitrary x naught initial condition. You evaluate the f at that point. So this value is f of x0. And from here, you want to guess which way do I go and how much I want to go to get closer to the 0 point of x. So of course, which way I want to go is given by the sign of fx and also by the sign of the derivative. So if f is positive, derivative is positive, I want to go back. If f is positive, derivative is negative, I want to go to the positive side. If f is negative, derivative is negative, I want to go to the negative side. So basically, I should have the opposite sign of the product or ratio of fx and the derivative. Now, how much do I want to go? If I only have the local derivative, I can write fx as an approximate of fx0 and dx times delta x, right, which is x minus x0. That's an approximation by truncating Taylor series only to first order. And that gives me a linear equation to solve for x. I know this is not exact because the Taylor series is truncated, but it gives me an x. That x is equal to x0, okay, minus f. So if this is 0, I want to move this to the other side, and what I have is fx0 divided by df dx, right? Because this is not exact, I want to say this is my x1. This is my next best guess of where the solution is. And the good thing is, the closer I get to the true solution, which in this case I'm going to be here, the closer I'm to the true solution, the more accurate this Taylor series is. Right? The residual is proportional to delta x squared. So the interesting thing about Newton iteration is that the more I converge, the faster I converge. it's a little bit different from all what we have looked at before. For discretizing PDEs, our error decreases like delta x to a certain power. It's a polynomial rate of convergence. For solving linear systems, as we have done the spectral analysis, right, the error goes down to the spectral radius of the iteration matrix to the kth power. So we have exponential convergence. Although we have seen in cases where the exponential convergence can be slow, very slow for Jacobi with a large grid, or very fast for multigrid. For Newton's iteration, we have what's called the super exponential convergence. In the sense, like even if I draw the residual versus number of iterations in a semi-log plot, if I have polynomial convergence, I would have something like this. I would only get a line if I have both axes to be in log scale. If I only have one in log scale, I would get a line that goes like this. So this is polynomial convergence. If I have exponential convergence, I have a straight line. And for Newton's iteration, I should see something like this. So this is Newton. If you ever implement a Newton's method and see you only converges exponentially, you probably have a bug in computing your derivative or your f. All right. So for true Newton's iteration, you should see a super exponential convergence. And this actually generalized to vectors. So if you have a system of equations, and of course here you have a system of equations, my x1 would be x0 minus, okay, now the df dx is no longer a number, right? It's a what? It's a matrix. So I have to invert a matrix. Partial f, partial x. Inverse times fx0, right? fx0 is a vector. I have a matrix, inverse times a vector. So here it's solving a linear system. And solving a linear system may be doing the green thing here, right? Solving a linear system may be just using iterative method, preconditioners, and things like that. And then it's just to get me a better guess. And then my x2 would be equal to x1 minus df dx. Now this df dx is different. It's linearized at x1. This is linearized at f1, right? So the previous one is you take the derivative at x0. Here is you take the derivative at x1, and etc. Right? So xk plus 1 is always equal to xk minus the Jacobian. This is what we call the derivative of a vector with respect to another vector. It's called a Jacobian. So this is the Newton's iteration. In every iteration, I may have to solve a different linear system, and solving the linear system may involve these iterative methods we talked about. So expect a lot of loops if you are solving PDEs, right? We have said that, okay, so in the smoothing, right, we may be looping over the I index, J index, if you have 3D K index. So you have 3 iterations, 3 levels of loops within this, and then you have 4 levels of loop out of this. So you may get a maximum of 7 loops, one inside another, if you're solving nonlinear equations with this kind of methods.